All right, this is section 5.2, probability rules. Let's get going. All right, sample space. The book gives a great definition of the sample space, and I'm going to give it to you right now. A sample space is all possible outcomes in a chance behavior. Okay, so real specifically, if I'm tossing a coin in the air, what I want to know is in this chance behavior of tossing a coin, and remember, a chance behavior is like tossing a coin or rolling a dice. Okay, what are your outcomes? Okay, and then you can get a head or a tail. I'll abbreviate that. And that is it. This is your answer. Okay, if they say how many outcomes in your sample space, then you would just say 2. Okay, now they don't always ask how many are there. They usually say what are they, and in this case, again, you just write H and T, heads and tails, if you like. Okay, 2 coins. Okay, so here's the thing: we got to toss 2 of them. Okay, so I've got H and T, H and T. And so we have heads, 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 tails. If you do this, just follow the arrangement from the top to bottom. Then we also have tails, heads, and then tails, tails. Okay. And so in this case, we have 4 outcomes in the sample space. And if we have 3 tosses, so we have the first toss, we have the second toss, and we have the third toss. Okay, so again, we have heads and tails, and each one of those items has an H and a T, and then those can all be paired up with a third toss of an H or a T. Okay, and then starting from top to bottom, we can list all the possible outcomes. If I count the bottom row, 1, 2, 3, 4, 5, 6, 7, 8, you can see there's 8 possible outcomes. So I have heads, 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 tails. Okay, as I went this way, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay, so here there are 8 outcomes, okay, in the sample space. All right, now, while this is coin flipping, know that if I talk about, I'm gonna put this up here, true false test, you're gonna have the same representation, okay? The probability of getting a true versus a false, there's only 2 outcomes, and assuming that they're equally represented, if you were going to submit a true false test that had 3 questions and you were gonna guess at the answers, how many different ways could you answer a 3-question true false test? Instead of having, for example, all these H's and T's, you would have T's and F's, but they would start the same way. You'd have false and true, false, true, and then you'd have the third line that looks like that with F's and T's, and you can make the same type of arrangement with your F's and T's as you would the H's and T's, okay, for true, false. Same thing with maybe a new couple deciding to have a family and they have children. Maybe they decide to have 3 children and are able to. Okay, but what's the arrangement of genders that you could have? You know, you could have boy, 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 girl, 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 boy, girl, etc. And you can make the same type of diagram and the same type of results using B for boy and G for girl as you would for H's and T's for heads and tails. Okay, so sometimes you'll see ones with children, okay, or a true false test, and you think, wow, these are different from what we've done, and they're really not. They're the same as the coin flips. You're just using different letters for their respective representation. Okay. All right. Now your sample space for rolling dice looks like this. I'm going to use a different color here. I'm going to use blue. And just some things to notice. One, there are 36 outcomes, okay, for this sample space. Okay, when I say sample space, that's one for rolling 2 dice. All right, and things that I want you to take note of. Let's say I want to look at the sum of getting a 6. Okay, so the sum of 6. So first thing I want you to take notice is that a 5 and a 1, like you see up here that I'm marking in blue, is different than a 1 and a 5. Okay, so 5 and 1 are different from 1 and 5. Okay, and the reason why, and this is why the dice are colored with reds and greens, is that your red dice, for example, could be a 5 and your green dice could be a 1. And over here, your red dice could also be a 1 and your green dice could be a 5. Okay, and those are considered unique outcomes. Okay, you can also have 2 and 4, and 4 and 2, those are unique. And notice this in the middle. I've got this, oops, sorry. I've got this 3, 3 that I wanted to highlight before I scribbled out the other one. I'll put this in yellow. 3, 3. Okay, and that's an important one right there because that is also an answer. I'm going to make that look dark there, 3, 3. But notice that I don't do the reverse of that. I don't put a reverse representation, right, 3, 3 twice, okay? And the biggest reason why there's not another 3, 3 in my sample space here. There's only one. So sometimes people get in the habit of saying, hey, if 5, 1 is a member of the sample space, then so is 1, 5, okay? Or if 2, 4 is, then so is 4, 2. 3, 3 works, but the flip of that does not exist in here. There's only 1, 3 within that sample space. Okay? Excellent. All right, decks of cards, or a deck of cards. This is your entire sample space. It is big, all right? And things to notice is that there are 4 suits. Okay, there are, and I'm going to put this color-coded well. There are spades. I'm going to put this right here. Spades look like this guy, this symbol right here. And then we have clubs. Okay. And then the 2 suits above that are diamonds. Okay, and then of course we have hearts. And amongst each of those suits, we have 13 unique symbols that you'll see in the corners of those cards. And most of the time, you'll just see these numbers like 2 through 10, okay? But for the ace, which is oftentimes symbolized with the number 1, or a value of 1, excuse me, you'll see an A instead, okay? And while typically jacks have a higher ranking than a 10, and the queen have a higher ranking than a jack, and then so on with the king, we don't label those with 11, 12, or 13. We just say, hey, that's a J, that's a Q, and that's a king, K for king. Okay, so there are 13 either numbers or letters that are positioned in the corners of your cards for each of the 4 suits. Okay, so in the end, there are 52 cards within the sample space. Now, I used to believe that everybody knew about cards, okay, and everybody played cards as a kid with, in my case, it was like grandma, grandpa, etc. However, I've learned in time that there are some families that just didn't play with cards when they were kids, and there are some cultures that just never played with playing cards. So if you're one of those people that did not have experience playing with playing cards, it doesn't hurt to go out and buy a deck and to just kind of look through the cards so that you can see how these members of your sample space are represented in your playing cards, okay? All right, we'll talk more about these in a bit. All right, probability. Says let X be the event of tossing a head on a coin. Okay, so and it says right here you're going to flip it 2 times. So I'll do this real quick. We have heads and tails. There's your first toss. And then your second is also going to be a head or a tail. And I'll match it up with each of the first possibilities. So you get heads, 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 tails, tails, heads, tails, tails. Okay. And so if I say, what is the probability that x is equal to 2? Then let's see. Well, there are 4 outcomes in my sample space. Okay. And how many of them have exactly 2 heads on it? Well, man, I'm looking at all 4 of these and I'm only seeing 1. Okay. So my answer is 1 out of 4. You can write that as 0.25 if you want, but that's really all you need to do. Okay. Now with 3 coins, and you can look on your note sheet, you have all the answers to that. We wrote those all down. I'll rewrite them real quick so that we can look at all the solutions to the sample space of 3 tosses. And let's go with tails. And there's your 8. Okay. Now, of these 8s, how many of them, let's look at what x is equal to. Again, getting 2 or more heads. So that means that you can have 2 heads or you can have 3 heads. So here are your 2 heads. Here are your 3 heads. So there's 2, there's 3. These have 0 heads, and each of these have, look like 1 each. So these are good. So there's 4 out of 8, which reduces to a half. Okay. People are like, do we have to change it to a decimal? And you don't. Okay. So if I'm going to write this symbolically nicely, we would get this. Cool. All right, let's keep going. Let's talk about outcomes on a pair of dice. Okay, so we'll let y be equal to the event of rolling the sum of the sides facing up on a pair of dice. And what I want to know is, what is the probability? Wrong spot. What is the probability that your y is equal to the 8? Meaning that if you were to roll a pair of dice, that the sum would give you exactly 8. Okay, so 8. If you look down here, I can write on this. Here are some outcomes that give you 8. I'll put the diagonal in that shows that. Every diagonal has a unique sum. And so in this case, we have what looks like 6 and 2, 2 and 6, 3 and 5, 5 and 3, and then 4 and 4. Okay, so we have 36 outcomes, and it looks like we have 1, 2, 3, 4, 5 that work. Okay, and you can just leave it at that. That's all good. Okay. Okay. X is less than 8. Okay, so what does that mean? That means, well, that could mean, I'm going to write this down here underneath the 5. It could be a 2, a 3, a 4, a 5, a 6, or a 7. It cannot be 8 though, okay, because 8 is not less than 8. 8 is actually equal to 8. Okay, so these numbers are what I'm going to look at in terms of sums. And remember that you don't really have a sum of 1. Okay, you can have a sum of 1 when you roll 2 dice. Okay, so that doesn't exist. So how many ways can you roll a 2? Well, here's your 2 right there. I'm circling that in green. It's just a 1 and a 1. There's only one way to do that. How many ways can you roll a 3? Well, here's my first diagonal with more than one item. You can do 1 and 2 or 2 and 1. There are 2 ways. 4 and 4. You got 1 and 3, 3 and 1, and then 2 and 2. There are 3 ways. 5 is 1 and 4, 2 and 3, 3 and 2, 4 and 1. So there are 4 ways. If you look at 6, okay, you got 1, 2, 3, 4, 5 ways. And the 7. That's my pointer here. Oh, there we go. Okay, so 7. It's the most represented one. You have this corner one right here, then boxing 2, 3, 4, 5, 6. Okay, now Out of 36 ways, these are all the possible outcomes of sums. And we want to add up all the combinations for each value. And so I have 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, looks like 21. Okay, so the probability, and this is again for number 4, of getting a value less than 8 with a sum of a pair of dice is 7 over 36. Oh, sorry, 21 over 36. 3 goes into each of those, so you could say that's 12, 7/12 if you want, but not required. At least not in my class. SAT tests or ACT tests or even on your AP multiple choice, they'll probably be reduced. Okay, so it's not a bad habit to get into. Okay. All right, the last thing, it says if 2 dice are rolled, what is the probability of rolling a sum of 1? You'll notice that there's not a sum of 1 anywhere on this sample space. The highest sum that we have is 12, and the lowest sum that we have is 2. So the probability of getting a sum of 1 is 0 out of 36. Okay. All right, so that is your dice. All right, we have 2 vocabulary words that are important for this class. One's called mutually exclusive, also known as disjoint events, and then also one called complements. All right, let's talk about each one. And I'm going to move my picture down a little bit so you can see the sample space for our deck of cards a little more clearly. But mutually exclusive, let's talk about that. Those are 2 events that have no outcomes in common. Okay. For example, let's say I pick a card from a deck. Okay, and I say, hey, what's the probability of A getting a heart? Let's let B be a club. I stated my question kind of bad. Go back to this. Let's let A be the event of having a heart, B being a club. I'll say, hey, what's the probability of having both occur? Okay, what is the probability of having A and B occur? Okay, now remember and is the symbol sometimes. Okay, it's your intersection. And if you look at this, the probability of A and B, well, is it possible to grab a card that has both a heart and a club on it? No, it's like 0. And so mutually exclusive events have no outcome in common. So for example, getting a heart, okay, and let B be getting a club, those are mutually exclusive events because you can't pull a card with one event and have both of those outcomes occur. Okay, so this is a good formula for that, for mutually exclusive events. P of A and B is going to be equal to 0. Okay, so those are mutually exclusive. Same thing, I can pull a card out and say, what's the probability that this card has both a 7 and a king on it? Can't happen. Can't pull a card that has both a 7 and a king. Those are mutually exclusive events, 7s and kings. Okay. All right, what's the complements? The complements of A, for example, is the event that A does not happen. Okay, so it's basically, I'm just going to write this. If this is A, okay, then the complement is basically not A. Okay, so if A is a heart, okay, which we had up here, A complements, you don't say it's a club, you say it's not a heart. Okay, because that can mean a lot of things. What is not a heart? Well, if I look up here, it is a club, it's a spade, it's a diamond. Okay, so and that's much bigger than just saying something that's not a heart, like a club, a single thing. So be careful of that. All right, now knowing these 2 items, these 2 definitions, and you have to be fluid with those as you not only work through these questions, but ones after this in your homework and on your test. Okay, let's look at these simple probability questions. It says, let W be the event of choosing a king from a deck, and let Z be the event of choosing a heart. Okay, and finally it says, let V be the event of choosing a 7. Okay, so what is the probability of W, meaning choosing a king? Well, I have 52 cards in a deck. Okay, W is a king. How many kings do we have? Well, I have a king of hearts, a king of diamonds, a king of spades, king of clubs. These are all kings. So there are 4 out of 52. And you can reduce that to 1/13 if you like. Okay, you don't have to change it to a decimal. Z is the event of being a heart. How many hearts do I have? Well, I look on top. The number of successes from a deck that would be a heart. Looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 52. Now, some of you who have played with cards before would say to yourselves, you know what, I know that 1 out of 4 cards is a heart. Can I just write 1/4? You bet. Okay, sure you can. It says, are W and Z mutually exclusive? Okay, there's W, there's Z. W is, just real briefly here, is a king, and Z is a heart. Okay, are these mutually exclusive? And the answer is no. They're not mutually exclusive. Let me see if I can make an M out of that. Okay, and the reason why is that if you look at your king and you look at your hearts, there is a card that actually has both. Okay, so a king of hearts does exist on one card. And I'll say this, if you're a card player of any type, writing a heart in the color green bothers me. So I'm going to change that. Not because what I wrote was wrong, just because it should be in red, and it just makes me feel better to have that. Okay. Okay. Assuming that makes sense, we'll move on. W and V. Remember that W is a king, and V is a 7. Is it possible to have a card that has both a king on a 7? And so you'll look at the 7s are all here. Here are all your kings, and none of these sets, either if it's looking at this or this, has a king or a 7 overlapping. Okay, so these are not mutually exclusive because okay, so no card, no single card contains both a king and a 7. Okay. All right, finally, this is Z. Z is a heart, and Z complement means not a heart. Okay, and so if I think to myself, of my 52 cards, okay, how many of them are not hearts? Well, I just said earlier that 13 of them were hearts. Okay, that's right here. And so what I'm going to do is do 1 minus that. So 13 are hearts. If I do 1 minus this, then I will get, let's see, 52 over 52 is the same as 1 minus 13 over 52. And that is 39 over 52. If you reduce that, you do get 3/4. Okay. If you want, you can always go to the reduced answer that you started with and use the same formula. The probability of, for example, A complement, I'm just going to use lowercase a just to be general here, is just 1 minus the probability of A. Okay, so if you had this 1/4 as the answer for Z, then the probability of Z complement is just 1 minus this answer you had earlier. Okay? All right. Again, be fluid with these. Mutual exclusive, again, two events that have no outcomes in common. Okay? And your complement, again, is the event A that does not happen. Okay? If you have the complement of A, that means the event that A does not happen. All righty. Let me move up here. Get out of the way of my problem. My little boy his name is Jackson, and he goes trick-or-treating, and he opened up his little M&M bag and he counted a bunch of M&Ms, 74 of them, and he separates them by color, which I think a lot of kids do. And here's the idea. If he blindly chose one M&M at random, what is the probability of getting a red? Well, if there's 74 to choose from, let's look at like how many reds there are. There are 12. And if you want, you can reduce that. That is 6/37. Okay. If I consider green or brown, let's see, there's 74. Green is 11. So I'm going to say 11 plus. Now, it doesn't tell you how many brown there are. And unfortunately, I don't know if this is brown, dark red. Sorry, we use black. Browns are unknown, but let's think about this. There's only so many colors in a bag. In fact, there's only 6. So if we know that there's only 6 colors, okay, we have 11 plus 13, which is 24, plus 12 is 36. 36 plus 18 is 54. So we have 54 of these 5 colors. How many are left to give you that remaining, to get to that 74 count? You have 20 more. Okay, so that means there are 20 brown. Okay, so 20 plus 10 is 30, 38, 50. And if you add those to it, you do get 74. So I will add 20 to this, and that gives you 34/74. Okay, brown or green. And remember, or means you'll add them both. And if you want to reduce that, that is 17/37. All right, the complement of yellow, which means what I want is not yellow. Okay, so it's 1 minus probably, the best way to say it is the probability of yellow. And so how many yellows do I have? I have 10 out of the 74. And so if I have 74/74 minus 10/74, that is 64/74. Again, you can reduce that if you want. That would be your final answer. Okay, so sometimes they don't give you the total number of every color. Sometimes you'll have to do a little problem solving to get to this last piece. Notice that we did add complements to this, okay, so be careful of that. Sometimes they have or, and if it's or, you have to include both pieces, okay, in your sum that it would appear in your numerator. All right, legitimate events. I like these even though they're a bit awkward, okay? Legitimate events means this. It means that the sum of your probabilities must equal 1 and nothing else. Okay, they do not have to be fair, and that bothers people because we're talking about legitimate. Okay, they do not have to be fair. So if I look at part A, it says for a coin, the probability of a head is 0.4, the probability of tails is 0.6. You have a weighted coin, okay? Doesn't matter if it's weighted or not. As long as the sum of all the outcomes in the sample space equal 1, then you're golden, okay? So you've got 0.4 here, you've got 0.6. Do they add up to 1? Yes, they do, okay? And what that means is it is legitimate, okay? It doesn't matter if it's not balanced right. That's not the point of the question. Legitimate just means that the sum will add to 1, okay? All right, for a single dice, now a dice, or one die, has 6 sides, and you can see that the first, the probability of getting 1 is 0.1, probability of 2 is 0.4, then 0.1, 0.2, and 0.1. And all I want to know is, do these add up to 1? Okay, so 0.1 plus 0.4 plus 0.1 plus 0.2 plus 0.1. So 0.1, 0.4, 0.1, 0.2, 0.1 is I think 9. And is 0.9 equal to 1? And that's a big no. Okay, so if that's no, then it's not legitimate. All right, last one. You have a spinner. I don't know if you know what this looks like, but it's like one of those round things you see in a game. That looks like a peace sign, but then you have the spinner in the middle, and you take your finger and you flick it, and it spins around, etc. Okay, and what they say is the probability of having it land on a 1 versus a sector of the 2 versus one that has a 3 on it. If you add them all up, you get. Now we have to be careful. A lot of people want to look at this and say, yeah, that's equal to 1. Not quite. This is not 0.3 with a hat on it. This is just 0.3. Okay. So what that means is there's maybe some other space on here that we don't know about that's not labeled, and in the end, yeah, it does not equal 1. So I'm going to put a big not equal to sign there, and that is not legitimate. Okay, and again, there's an assumption here that maybe there is another sector that we don't know about. Maybe this is 0.3, maybe this is 0.3, but maybe there's a fourth one we don't know about that gives you that extra 0.1. Okay. Excellent. Okay, let's keep going. Again, they just have to equal 1. Sum must equal to 1. Doesn't have to be fair. This bothers people because they want it to be fair too, but it doesn't have to be that way. Okay, general rule. Okay, and here's what we got. If there's two events, A and B, resulting in some chance process, then P of A or B is equal to P of A plus P of B minus P of A and B. Okay, and here's what it reads. The following number of customers ordered a given slice this past weekend at Costco. Okay, and let's imagine that we went up to one of these customers who ordered a slice and we asked them one of these questions on the bottom. And before we do that, though, what I want to do is I want to sum up all of the columns, okay, and all the rows. So if I look at this here, this is 460. Okay, if I look at this one here, this is 740. If I go across, it looks like that is 600, as is this one. It's also 600. And if you add everything up, going horizontally here, that is 1200. And vertically, it's also 1200. Okay, so here's what it says. It says, what is the probability of random customer who ordered a slice of cheese pizza? Okay, so it's assuming that the person ordered a slice of pizza somehow. Slice of cheese. Well, there are 1,200 total people who ordered a slice of pizza, and of those, 460 ordered a cheese. Okay. All right. And that's all you have to do. It's pretty simple, basic probability, but again, you have to add all these up ahead of time. What is the probability that a random customer who ordered a slice of pizza ordered on a Saturday? Okay, now we have people who ordered on, well, Saturdays and Sundays, so we're assuming that we're picking a customer from the weekends, okay? And from a Saturday, you can see that there is 600 people who ordered on a Saturday. Okay, and that does reduce to a half. That's not my number one concern when we have fractions that are this big, okay? All right, next one says, what is the probability that a random customer ordered a pepperoni slice on a Sunday? Okay, so here's the idea. If A is the event of ordering a pepperoni slice, okay, and we'll say that B is the event of ordering on a Sunday, what is the probability of having A and B? Okay, because it has to be both. It has to have a pepperoni and on a Sunday. Well, again, I have 1,200 people who ordered a slice of pizza. And of those, pepperonis and Sundays, looks like this number is right here in the middle. Those are the amount of people who have both a pepperoni and on the given day they're asking for, which is a Sunday. So that's 380. Okay, if you want to reduce that, you can. Okay. All right, and the last one is the probability of getting a pepperoni slice on a Sunday. Sorry, let me re-say that. What is the probability a customer who orders a slice of pizza eats either a pepperoni slice or order on a Sunday? Okay, so you have to satisfy this one or this one. or potentially both. Okay, if you satisfy both of them, then you at least satisfy one. Okay, and that's considered okay. So instead of having an and, I have an or, because that's what's written here, or. Before you start thinking too deeply about it, go up to our formula above. I'm going to highlight this here in another color so that you can see it a little more easily. I'll put it in yellow. So there you see that in yellow. And I'm just going to write the outcomes for a P of A plus a P of B minus P of A and B, which is part of that formula that we're using today. Now, probability of A is just the probability that we had a pepperoni slice. So pepperoni total is 740 out of 1200. Okay, that's this piece here. I'm putting this in blue. I'll do this next part in purple. The probability of B is just ordering a sundae. So sundae is 600 out of 1200. Okay, and the last one is the the and piece, which is this back piece, which I'll put in red. Okay, so I'm color coordinating everything down here. P of A and B, you're like, what's the probability of having a pepperoni slice and a sundae? Well, you answered that right here. Okay, and so that was minus 380 over 1200. Okay, so what is that total? Well, because I want to make sure this is right, I'm going to use my calculator, and there is no shame in that. So 740 plus 600 minus 380 gives me 960. Okay, and if you're not sure how I got each of these three fractions, look at the items in blue and purple and red based off these respective colors. Okay, and now remember that we're also referencing this right here. This is what our definition was for event A and B. All right, so 740, let me just check this once more. And do this again, 740 plus 600 plus, not plus, minus 380. Okay, I think we're good. All right, so be careful of that. There's a difference between and or, and this and is kind of implied in the third question here, whereas or is really defined, but they have a different answer for each one. Okay. All right, this is our final question. It says the following event describes 900 Perry High School seniors who are applying to in-state universities. We're going to use some Venn diagrams in a minute to help answer this question. We're going to let A be the number of students applying to ASU, Arizona State University, and N be the number of students applying to Northern Arizona University. Okay, and here is a representation, a table that shows how many outcomes that we had for each of the respective schools. Okay, ASU is listed here on the upper piece, and on the left is NAU, and you can see the totals for each. So when you read this first one, 520, that means there's 520 students who applied to both of these schools. Okay, this 150 here under each of the two no's means that there are 150 students that didn't apply to either. Okay, this table that you see here is called a two-way table. Sometimes they'll give you problems and they'll have you create a two-way table to help organize your data, if that makes sense. Okay. Now, what we need to do, like we did before, is add everything up. So I know that this is 660. This is 240. This is 610. I did that right. And this is 290. Okay. If you add up horizontally and vertically, you should get the same total, and it is 900. Okay, now, Venn diagram. Trying to draw my circles clean. All right, and this will be event A, which is applying to ASU, and this is event N, applying to NAU. And let's put some different colors in here to make this stand out a little bit different, a little bit better. And what we have to consider is the intersection first. I always do this part first, and it's important for students, I feel, to do the same. I always fill this part first. Okay, and that's the part they have in common, meaning how many students apply to both ASU and to NAU. So if I look at those, that is represented by what you see here in blue. Okay, I'll just box this up. That's 520 students. Okay, so 520 applied to both. Okay, how many people apply to ASU, which is this part here, but notice that is not an NAU part of the circle. So this means this part in red, only ASU. Okay, let's see. That would mean that, well, 660 total applied to ASU. 520 of those people applied to both. If you take the 660 that were part of ASU, and you take away the part that was the both, and the both was 520, then you would finish with 210. Sorry. 660 minus 520, you'd finish with 140. I don't know where I got 210. I'll rewrite that in a second. And notice that number is right here, 140. So, okay. Just want that to look nicer. Okay, and then similarly, I want people who only apply to NAU. Well, if all the people who applied to NAU was 610, NAU, and I'm taking away the ones that said yes, minus 520, then you're finished with 90. And notice that that's this number right here. So I'll put 90 in this spot. And there's one more number you have to fill in. And so you have people who only applied to ASU. That's this part right here, the part on the left. The part on the right are the people who only applied to NAU. The part in blue are the people who applied to both. And I'll put this one in black. The one on the outside here, I'm going to write this with a 150. Okay, I know there's a total of 900 students who are seniors, but the 150 is the people who applied to neither. Okay, and so I'm going to represent that one as well. All right, so we drew the Venn diagram for the 900 people. Okay, and now we're going to find P of A. What is the probability that if I were to pick a student from the senior class, that A is applied to ASU? Okay, so how many applied to ASU? Well, it looks like total there were 660. Now notice I didn't say only ASU, I just said ASU. So if you applied to other schools as well, as long as ASU was one of them, that was considered a success. Okay, so you have 660 over 900. Probability of NAU, well, let's take a look at NAU. There are, how many students applied to NAU? It looks like 610 if you add those up, or if you just look at this guy, 610. Okay, over the total amount, which is 900. Okay. A union N is A or N, which means you had to apply to ASU. Let me just write this underneath. ASU or NAU, okay, or both. Okay, as long as you satisfy at least one of the two, then that counts as a success. Okay, so how many is that? Well, it's the 140, okay, plus the 520, okay, minus the, plus the 90. Okay, so when I look at the Venn diagram, that's how I read it. Okay, all over the 900. Okay, and I think if you add all these up, you get 750. I'm going to put this a little bit higher so you can read it. 750 over 900. If you want, you can use the formula that we used just a little bit ago. I don't think the formula is wise to use when you have a Venn diagram, because I think that's why we do write a Venn diagram. In this case, it's N. But basically it's this. Remember, it's P of A plus P of N minus P of A intersect N. Okay, and so what is P of A? Well, it's all ASU people. It's right here. Okay, this part under A. It's actually question A. Okay, so that is 660 over 900. Your P of N is, well, it's part B, what you did, 610 over 900. And remember, the intersection is the part they have in common. It's actually this piece in blue. So my blue marker isn't out right now, but it's 520 over 900. And if you did the math, you would get the same thing. So the 900 is still on the bottom, the 750 is on top. All right. So there you go. Either way is good. I would say in general, they prefer that you do it this formula way, the way I did it the second time. However, when you do a Venn diagram, to me, it's easier to look at the drawing to help answer the question rather than use the symbols for the formula too. But that's just my opinion. Okay. I like question D because we've already answered it. It's actually the last piece right here. So it's this piece right here. So it's 520. Those are the amount that signed up to both, 520 over 900. The complement of A. What is the probability of the complement of A, meaning not ASU? Okay, so what is that? Well, it's basically the probability of just A, 1 minus that. Okay, and so do I know what that is? Yeah, that's this piece right here. It's A, helps us get that. It's 1 minus the 660 over 900. Okay, and what does that leave me with? I think it leaves me with 240 over 900. Fine. Okay. And again, I don't care if you reduce it at that point. You know, if you can show me mentally what this means, that's really what's important. Okay. So again, the probability of A complement just means 1 minus the probability of A. Okay. I find the probability of not ASU. And so if I know ASU exists here, there's the other piece. Okay. All right, 2 left. They're a little complicated here. And sometimes I make my own Venn diagrams with these just to make myself understand this a little bit easier, okay? If I ask for the probability of A, so I'm just going to draw this piece first, P of A. I know it's going to be out of 900, but let me just look and see what A is. A is everything that you see to the left in that circle. So I know that A is everything that I see here. Okay, and if I needed to, I'd make a probability of that. If I did not N, okay, so N is the circle in the Venn diagram on the right. So there's your N. If I said not N, okay, I get this. And if I ask for the union, sorry, the intersection, which is this item in the middle, let me circle this in a different color so that you can see it well. This will be purple. What I want to know is, what does this have in common with that? What does this first Venn diagram have with the second one? Okay, if I'm looking at the two that I just drew, okay, what part is equally shaded or shaded in the same region? What regions are shaded the same? Okay, ask that question like 4 different ways. Okay, but again, their intersection is basically the part they have in common, which is this part right there. Okay, and what is that? Well, if I look above, that is the 140. It's basically only A. You just want A with no N in it. Okay, so it's you want people who apply to ASU, but only ASU. Okay, and that's out of 900, of course. All right, here's the last thing. And I'm going to do this the same way. I'm going to make some pictures here because I think that helps me answer these more easily. And I'm going to do one for each piece. So this one's going to go here. And this one is going to go right there. And if I say not A, well, I know this is A. Not A means I'm going to shade everything around it. Okay, so it's basically everything but the A. And if I say not N, it's just going to look the reverse. Okay, and what part do they have in common? This looks kind of weird, but it's basically anything outside the circles. Okay, including the intersection. The intersection is not part of it either. Okay, so not in this, not in that. Okay, and again, so any part that overlaps the shading between the first group and the second group gives me what I see here. Okay, and what is that? Well, that's the, I hate to draw a million lines here, but it's this 150. Okay, it's what you have on this outside. You didn't apply to either school, basically. Okay, and you'll write it like that. All right, that is the end of this section. I hope that all made sense to you. If not, you can rewind it, rewind the video, look at it again. If you have any questions, ask your teacher, or you can ask me, and I'll be happy to help you out. Otherwise, I hope you have a great day. Thank you. Here's your assignment.